Damn, it's Monday. So let's see if today we can solve another coding problem under 40 minutes and then debug it for a couple of hours or so. So this stream is for entertainment purposes only. Let's see what we've got today. So there is an interesting button on the Google search page called I'm feeling plucky. So I have no idea what does it mean. Feeling adventure. So what it does, I don't understand. Should I click on it? Feeling plucky. Ah, so it gives you a random search. Interesting. Anyway, so let's see what's the problem is. Pick one. And this is medium. Oh, and a lot of people like it. So maybe it's a good problem to solve, and we'll see. We'll see. Possible bipartition. Given a set of n people numbered from 1 to n, we would like to split everyone into two groups of any size. Each person may dislike some other person, and they should not go into the same group. Formally, if dislikes A and B, it means it's not allowed to put the people numbered A and B into the same group. Return true if and only if it is possible to split everyone into two groups in this way. It's interesting, right? So okay, I see two couple of ways how to tackle this problem. It's not super hard to solve, but there might be interesting approaches, and I'm not sure which one will give us a good performance benefits. So let's switch to the whiteboard. All right. So what basically we asked to do is to say so basically let's do the opposite, right? Let's say we have some random people. And now let's say instead of specifying with whom these people may connect, we will specify all the people with whom they may not connect. All right. So, so let's say, all right, so let me undo this. Select this marker. So let's say these people are okay to be with each other, right? And they don't, this guy doesn't want to be with this one. This guy doesn't want to be with this one. This doesn't care, can be with any. Okay. So let's say this guy is also okay to be with this guy. I see. Right, so they're okay to be with each other, and obviously they're against to be with everyone else. Maybe not. Maybe this guy is also against to be with this one, Because I think this is symmetrical or not. Okay, it doesn't really matter. So it's kind of symmetrical. So let's imagine these guys are okay to be like this. All right. Which means we can have this group and this group. Or we can have this group, or even like this group and these two. So what do we need to check? Um, I guess it's basically like a union kind of thing. So we start with n sets where every set contains one element of one guy in it, right? Because obviously everyone is okay to be with it. And then we're trying to merge them until the point where we have only two left. And if we can, then we return true, otherwise we return false. So how it works? So imagine, so we have these bubbles of 1, 2, 3, 4. Then we go in, so we split it like this, right? Then on the next step, right, we do one step, we go in linear time, and if two of these, if the pair of these two is not in this guy, we merge them. Same for everyone else. Is this how it works? Still doesn't look obvious to me. Like it looks like yes, every time we will try to merge them, but we should be focused only on some halves of them, right? The problem is that if I want to merge, then I might be able to merge 1 and let's say 3, right? And I don't know this in advance. Or I can start by 1. I can merge these with let's say this guy. And then if I can also merge it with this guy, then I have 3 of them, and so forth. So the merge part is not obvious to me, but I guess it's one way of doing this. Another way would be, I still want to do sort of a graph approach, like DFS or something. Like this is basically like spanning tree, right? So we want to cover the nodes. We don't care about the weights between edges, but we just want to cover as much as possible until we cannot, right? And what do we do in this case? I guess we just start with one edge, then go to another edge, into another edge, into another edge. And number of all edges is actually n square, right? Minus size of dislikes. So like it's all possible combinations minus size of dislikes. So once we ended up with what is I wonder if we can, so obviously we can first create the likes, think, right? So what if, yeah, I don't see any other way rather than just merging them. All right, so let's try and see if we can do something like this. At least we can try, right? So to do this, we do want to, okay, maybe we want to find a way, first of all, how to check in constant operation that two can be put in one set. To do this, we might have unordered map. So n is from 1 to 2000. We don't need an ordered map. We may just have vector of sets, actually. It's even better, right? Vector of unordered set of integers. And again, to me, it's weird because n is from 1 to 2000. Do we really need it to be whatever? Dislikes map, let's say. It's not map, it's vector, but who cares? So we know that the size is n, and an ordered set n is just, we want to initialize every n with empty set, right? So initially no dislikes for everyone. And then what do? We do this for const autumn. It's not map, so we don't need this one. We can just say what pair in dislikes. And then we say dislikes map is pair 0. Insert pair 1, and vice versa, right? Pair 1, insert pair 0, because it's obviously if A doesn't like B, B also doesn't like A, so they can be in one set. Now here is the fun part that comes. We need to find out if we can split something in two. 3, right? Low is 2, dislikes from 0 to 10,000. It seems like if dislikes size is less than n, there is always a way how to avoid stuff. Yeah, all inputs are good, so we don't need to worry much about all these bad inputs. Dislikes are at most n. So let's see. Now our goal is to try to reduce this vector to size of only 2, probably, or something like that, or whatever. Let's have another vector of set. Also initially of size n, right? It's another set, and this will be, yeah, we don't need this one here. This will be what? This will be unions. And do something, and then return unions size equals 2, right? So first of all, obviously what we do is for int I equals 0, I less than n. Okay, so it's not from 0, it's from 1. So it's from 1 to less equal n. That's okay. That's okay. We can say n plus 1 just in case. Yeah. Vector starts from 0, so technically we need to say -1 all the time. Yeah, it's a little bit inconvenient, but who cares? So insert pair. Let's just always do -1, so we don't really care. And here we say also then from 0 to n and I plus plus, right? So what we say is that unions I insert what? Insert I, right? Everyone is okay to be with themselves, right? So, we're always fine with ourselves. We might not like other people. Merge. So how do we merge? So theoretically, Pref size let's say equals n plus 1 at the beginning, so we can enter cycle while union size greater than 2, and obviously if we can split it to 1, then so we can just say less or equal 2, and pref size is greater than union size, meaning that every time we do one cycle of merge, if we cannot merge anything, there is no way we can continue. We stop, and if union size still larger than 2 or 3, larger than 2, then we return false. Right, so it's obvious because all we need to do now is just, let's say, peak union 1, right? And, or whatever. Let's see which remove element can be done in a 1 from vector. C++, constant time. I think it's the front one. Erase. It's obviously it's n, right? But remove. Okay. Erase front in vector C, constant time. So pop back, pop front. Okay. So if we pop back, what does it do? For pop back, it's constant. Okay. So that's what we do. I just say auto next union equals to unions pop back. Does it return something? Return value none. So then we should say back. Back and then unions pop back. All right. So once we do this, all we need to check So what we do, we can do for, right? Let's say outer current union in unions, right? It should be -1 element already if you do pop back. It's a bool merged. It's a false, right? So we say previous size at the beginning. We say it's unions size, and if not merged, we can break actually, because we know, right, that it doesn't. We don't really need the size. So what's the point of it? We can just break ourselves. If not merged, break. So merge two sets in C++. I guess there should be a simple command. Set union. Interesting. Set odd, even. Let's say we have that's how we do it. Okay. Let's see. So we say car. We can say actually auto car union is it insert? Yes, insert next union begin and next union end. Right, so this operation is at most or and because we do this once, so we go and check, and once they match, we insert. So its overall iteration itself is O n. But we're removing this one by one, right? So it will take us, but we merge every time we remove, we merge. So number of elements will start reducing theoretically logarithmically with respect to the number of elements size, or one by one. If one by one that is quadratic, it's not really interesting. But hey, let's see. So, right, so we merge it. That this will be quadratic. So we go through all possible union combinations. If we can merge, we do it. Yeah, whatever. Okay, so let's think about complexity further. Not right now. And then it should be if can merge, right? We should say next union, current union, and dislikes map. Then we merge, and then that's it. So then now namespace of what bool can merge. We say what we say another send int const obviously, and union one, or we can say A and B for simplicity. B and this, then this thing, right? Const vector or something. And we say dislikes map, and we do something here. So, right. Let's see. So if at least one of those elements in between, right, is within dislikes map, then we break. So very simple. For const should we say union A and union B? A union B for const outer whatever union A should be A union A union A. Same thing here, but for union B. All right, in B. So return true, return false if what? If dislikes map A count B this, right? So if we contain the dislikes, we return false, otherwise true. And now it should work. So all of this is linear. So union size, but technically we reduce it by 1. So this goes to n minus 2. And every time we go through every union, so it's like n times n. It's quadratic solution. It's not like something, and it can be 10,000. So although we don't really care about dislikes length, we care only about n itself, right? So if it's 1, then obviously it will be 1. This one yeah, but the union size will be 2, will be 1, so it's okay. So we also need to say this, right? Because we know that we can merge, so we say merged true. So technically this is or n square, and I think it should be something more smarter than this. So let me check the Crucible version of the algorithm. It feels like, how much time we have? Like 34 minutes, so. For each vertices in graph, do make set, okay. For each, so that's what we did. For each UV in GE ordered by weight, increasing do. Find set U not equal find set V, then F is union of U and VU. And then we do union, find set U and find set V. Yeah, what about Prim's algorithm? So it looks like exactly what we're looking for, and it's agency matrix searching V square, binary heap, can be log. Let's see, Kurzko's algorithm CPP, just to make sure. Spanning tree. Pick the smallest edge. Check if it forms a cycle with a spanning tree formed so far. If cycle is not formed, include this edge, else discard it. Repeat step 2 until there are v minus 1 edges in the spanning tree. All right. Yeah, so what do we do? To represent disjoint sets. So we have parent rank, disjoint set, this and parent rank, blah, blah, blah. Vertices are in different sets and have rank 0. So it's like the opposite, right? So we can go through all this, like pick the edge between them so they cannot be placed, so we don't merge them. Otherwise, we do merge them, right? So it seems like they really want n times this. But let's see, first of all, if this code works. It's also merge, it's just not as interesting. And we don't need this anymore. Yes, you're right. So which one? It works, but I doubt it will pass time complexity check. But let's see. Oh, wrong answer. Interesting. It says true, but the reality is false. Oh, actually, what we should say, if not merge before we break, right? We should put back this is right one. Yeah, this is wrong. We should say unions push back next union, right? Should still work, and then now we shouldn't fail here. But this is okay. This is a corner case. When you exactly delete one and then, but how come? Unions push back next union, which means it cannot. Right, I do not understand it, but see out union size. I don't really understand why it fails again on the simple thing. Union size. It's weird, super weird. Union size 3, then 2, and we stop, right? Okay, maybe we should also print what are the unions here. It should take us some, but no, it's only through force cycle. I see it. Okay, whatever. So let's submit and see if the union size got to 2. So this means that can merge doesn't work. So wait a second. So if A count B, right? So if it has at least one element, then it should return false. So damn it. And the code still should pass. Now it does. What? Are you kidding? But you says 3 and 2 and then false. How come? How did you merge it to 2 then? It's because I didn't really. Okay. And then we just break eventually because we cannot merge anything. Although 1 and 4 should do the trick, but let's see. All right, A3, B0. So 3 and 0 means 4 and 1. They do not dislike each other, right? So it's okay. We pushed back, so we started with 4. Okay, I see. So then with 4 with 3, but this is it, right? So it's 0. So if it's 0, we return true. Can merge. We should say merge true, right? It should break here. You shouldn't try to merge with everything. True. Let's see if it works now. Yeah, it is. Let's see if it now can be submitted. Expected true but returned false. Oh gosh. 0, so we merge it, then we try 2 and 3 just like 0, so we merge 3 and 4. Right? Or no? I didn't get why we went through the whole cycle here to the last one. The first one was done. Ah, no, still don't understand. So it wasn't merged until this one, right? So we had 4 unions. The first time we removed 1, so it was 3. Then we start with 3, then it says becomes 2, and then we remove it. 2 is 1. 2 and 1 is 3 and 1. And 3 and 1 just like 0? I don't understand why. So 3 and 1, 3 and 1 dislike 1, true. 3 and 2, yeah, 3 and 2 dislike 0, that's true. But then 4 and 3 also dislike 0. So I don't understand why we move further here, actually. We can merge, true. Yeah, this way we won't debug it. Okay, so we run out of time, so let's just debug it to the end and stop wherever we can. All right, so we won't change the logic anymore in sense of time complexity or whatever. Failure again. Why? Why this debugging always fails? Merge true. And then next cycle we again start with false. Everything looks reasonable, but doesn't work for some reason. So let's say then we have another thing called print unions. Or for compactness, let's say this one. Then we say cout, what, closing bracket and new line, right? So then let's see at the beginning this thing. We say unions, cout, union size. unions, right? So that's how we print them out now. So at the beginning we have 0, 1, 2, 3. The next one is 3, 0, 1, 2. And then let's also print it finally before return, so we know what had happened and why. Three zero two one, exactly true. It says submit. So what happens here? I just wonder. So we start with union size 10. So it's from 1 to whatever, size 9. And then it's 90, 890, 6. Ah, should it be actually the opposite? I just wonder. I just realized. I think I know how to solve this problem. Maybe not. So can we say that if we have two groups where at least one person dislikes another one, no, it's not the same. So the problem is we may stop, let's say like in this case, we stopped at 5 because we added everything to the first one, and then there was no way how we split them further because at least one will be hated by these guys. So yeah, the algorithm doesn't work all the time. So it works in some cases, but not all the time. So we didn't solve it. And I think the reason is really you should do this dislike thing. So if they dislike each other, then let's say we combine them as one set. And if we have two sets of two sets that dislikes each other, it doesn't mean anything. Yeah, I don't know if you can transfer simply. So we start with one and split it in half. Then in another half. Can we merge now? Can we merge now? Can we merge now? Iterator. So yeah, I think we failed it. Let's just face it. We failed it, and it's dynamic programming, right? Let me just check. I just don't see. Breadth first search? Breadth first search. Interesting. So you were able to solve it with breadth first search. So returning back to the whiteboard, how on earth we will solve it with breadth first search? Right? We remove, let's say, all edges that are not connected, right? To the guy. So we do breadth first search almost similar, except the adjacent nodes will be whatever is not in the adjacency list, because those are dislikes. And then we mark it as so we color until the queue is empty, and then And then we color second one from those that were, yeah, you can solve it with breadth first search. Stupid merge. That was my initial idea. Whatever. Oh, can you? Whatever. So in my case, the issue is if I join some groups one way, I might not be able to join other nodes with anything. But maybe if I won't join first one in the first place, I would be able to join these guys as much as possible. Right. Okay, so we passed 33 out of 70. And we can solve it with breadth first search. So how you solve it with breadth first search? You marked first all nodes uncolored, right? You have a graph like this where you remove all edges that are in conflict, that are dislikes. And then you start like going through it like white, so I can be with this, 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 with this. This is, let's say you form one sort of a tree or forest, whatever you call it. Then once your queue is empty and some nodes are still uncolored, you check again. If it's uncolored, you pick one as root and go through another cycle. So, and if second time, after second time, all nodes are colored, then you say true. If not, then you say false. I think that's what it is. So, yeah, problem was simple. But damn, I didn't get it. Yes, visited, graph, which is vector of int and plus one. That's what I did actually with. So this guy uses depth first search. Okay. Whatever, depth first search, breadth first search. So graph think, and we failed the graph theory. This is funny. You're always using this breadth first search, depth first search, but sometimes you just don't see good application for them. Although we started as a graph, but for some reason we decided to go with unions and we failed. Let's go algorithm. Yeah, whatever ways like form two sets, you're always like, maybe union. But seems like not. So it's graph of dislikes, right? And yeah. Basically, the idea is It's BFS, but the opposite. So if you basically traverse everything except the edge that is adjacent to this node. Kinda obvious. Whatever, yeah, we get the problem. And of course, you haven't seen anything because I haven't seen the screen. So yeah, as you can see, a lot of people offer either breadth first search or depth first search or whatever, and we passed through 33 out of 70. So yeah, let's stop this useless streams with useless person trying to solve useless problems. Okay, so today we have 33 out of 70. Yeah, I don't know. My head just doesn't work today. Not sure why. But I'm degenerate, so it's okay. I guess 33 out of 70. So this was a good problem. I'm just not smart enough to solve the media problem these days. Right. So thanks and see you tomorrow.